Schiavone. I'm from ATH Zurich. I'm here to present DSP ISA extension for an open source RISC-V implementation. So let's start giving you an introduction. We have a typical embedded system. We have sensor, we acquire data from sensor, we analyze and classify data, and then we send that tag to the external world. We have sensor, then we analyze and classify data, and then we send this tag to the external world. As you see, in the embedded system, we usually have an energy-constrained environment, so we need to be energy efficient. That's why we built Pulp, parallel ultra-low power platform, that provides several hundreds of mega operation per second in a power envelope between 1 and 10 milliwatts. But today I want to focus on the core we are using in Pulp, which is based on the RISC-V ISA. So I introduced Riscy V2 core. Is an evolution of our Riscy V1 implementation presented during last workshop by Andy Traber. We support RV32 IMC ISA and plus some other extension to target energy efficiency. We support interrupts, exemptions, and we provide a debug. We have GCC supports. We provide profiling and core execution trains, and the core is meant to work in a tightly coupled multi-core systems. So we can say our microcontroller is actually competitive with state-of-the-art microcontroller. So here you see some numbers. The core marks per megahertz of our Riscy V2 is actually competitive with M4 by Cortex by ARM. And here an example of our previous exemptions. So we have an addition between vectors. It's a very simple kernel. And the baseline assembler is this one. So you have load instruction, store instructions. Then you have addition to update the pointers. Then you compute the addition. Then you have the counter and the branch instruction. With auto-increment load and store, you can get rid of the counter update because we have it inside the load instruction and in the store one. So we have from 9 instructions per iteration, 6 instructions per iteration. So both the code and the performance are better. And then with the hardware loop, you can just set up our controller, and then we can get rid of the counter and the branch instruction and execute the loop in just 4 instructions per iteration. Now we want further extend our ISA to target DSP application. So here you see 2 charts. In the x-axis, we have some benchmarks. So we have in this side control-intensive applications, so we don't really need mathematics inside, such Fibonacci or bubble sort. Or in the other side, we have data-intensive applications. So we have motion detection, matrix addition and multiplication, convolution, FFT, and as you see, thanks to our previous extensions, we already can have a speed up in performance up to 1.2 and 2 for control intensive and data intensive applications on average, and a peak of 2 and 3.9 for control and data intensive applications. So why DSP? The typical workload of our system is actually near sensor computing, so we need to speed up our DSP application such that we can go to the low power mode as soon as possible and so save energy. So we want to be energy efficient like this. You have a task. You can do that in a green fashion or in a blue fashion. As you see, the green one is shorter, so we can go to sleep earlier, but it takes more power due to the more complex hardware. But we care about energy, so we want the energy to be smaller than the other one. So we want an increase in performance higher than an increase in power. So that's what we implemented in our Riscy V2. We have dot product between vectors, saturation, addition, subtraction, and multiplication, plus round and normalization to handle fixed point arithmetics, shuffle operation between vectors, and then we implemented a packet sim LAU operation, so you can add, subtract, or compare vectors. So you can see our vector is a 32 bits, and you can see that you can see the registers as a 4 bytes element vector or two shorts element vector. and then bit manipulation. So you can set or extract a set of bits from a word. Here you see we actually have GCC support for that. We use GCC 5.2. And to use vector, you actually need attribute to tell GCC that this variable is a vector, and then you can add the two vectors. It's a standard GCC. And for not standard GCC, you have to use built-in instructions. So for instance, here you see how to compute the dot product between two short vectors. And as a normal, this is normally an embedded system, so this is the assembler generated by GCC. You see there the addition between vectors, and here the dot product. So to use our extension, you need to rewrite your C code. So here I want to show you an example for a 2D convolution. You want to convolve this picture with a kernel. Let's assume the kernel, the filter is a 3x3 matrix, and each coefficient is a 16-bit value, for instance, a Q1.15 fixed point number. So instead of doing 9 loads in 9 registers, you can just do 5 loads in 5 registers because you use vectors. And you can do the same with the current window in the picture. You see colors to see different vectors. Then you compute the dot product. And so in 5 cycles, each dot product takes just 1 cycle. And so after 5 cycles, we can commit 9 multiplication plus 9 addition. Then you sort the pixels back to the memory. Then you load the next 3 pixels, and you put in 2 vectors. Then you shuffle the purple and the white vector, such that you don't have to load again that from the memory. You don't need bit and mask instruction. And then you move back the window, where you do it again for each pixel in your picture. So you see in this side, we have the scalar version of pseudo-C code. So you have for each window in the picture, you compute the element-wise multiplications. Then you round the shift, for instance, to adapt the fixed point formats, and then you saturate, if you want to saturate that, and then you store the pixel back in memory. For a vector version, you need to load the 5 vectors from the filter. Then for each window, you can compute the dot product using the built-in. Then you have the built-in for addition plus round and normalization to do this operation here. And then the clip is inferred automatically because it's a standard GCC function. And so you don't need any branch there. You just use a clip instruction, and then you store back the pixel. Then you load the next 2 vectors, then you shuffle the vector, and then you move back the window. Here you see the same chart as before, but this time it's just focused on DSP benchmarks. You see motion detection, matrix addition, and so on. The blue bar is the scalar version in our core with the RISC-V 32IM ISA active. The green one is the same scalar version, but with our previous extension active. And the red one is the same kernel, but rewritten to use vectors and built-ins. And you see the speed up is quite good. We have, with respect to the original ISA, 6.4 increase in speed on average, and up to 9.5 for a convolution with a 5x5 matrix kernel. Here you see it's the same chart, but this time we compare our Riscy V2 with our Risky V1. So the blue bar this time is our previous extension, and the red one is the one rewritten with vectors. Even here we have a speed increase on average of 3.3 and a maximum of 5.2. Let's talk about post-layout simulation. We synthesized and we did the back end of our Risky V2 in 65 nanometers. We achieved a dynamic power of 30.6 microwatt per megahertz. The area is 67 kilogates equivalent using the NAND2, and the critical path is 32 gate equivalents using the inverted, which derives for other inverters. So running DSP optimized kernel increased the power, because you can imagine the dot products consume much more power than the normal multiplication, because it's a bigger multiplier, it's much more complex. But if you if you have a look at the energy efficiency, this time we have the same kernels in the x-axis, but this time we have energy efficiency on the y-axis. It's not just speed. So as you see, we have an increase of energy efficiency of 3.2, and as a maximum of 4.6. It was 5.2 for speed, but then you combine power and speed, and you have 4.6. That is good. So we built silicons. We made 16 chips with our open RISC implementation. But now we are doing our chips based on RISC-V. We have Honey Bunny and Imperio with Riscy V1. And by the end of the year, we are building Pulp 4 based on our Riscy V2. So there are several companies and universities that actually help us to build our system. We release just 10% of what we are going to release in the future. And we have companies and universities that actually are using our systems, and they are growing. We target mainly ASIC design, so we build chip, but we can also have FPGA implementation. Then we have also a Pulp SDK, so we provide an hardware abstraction layer to access, for instance, DMA or hardware synchronizer. Then we have an OpenMP runtime support, and we have also a virtual platform to model our system in software. It's written mainly in C++. And I want to say that both the hardware abstraction layer and the OpenMP runtime support is going to release in December. And so to conclude, we target typical signal processing algorithms, and we have a speed up of 9.5 with respect to the original ISA and 5.2 with respect to our previous Riscy V1. All of our extensions are supported by our compiler, which is going to be released in December too. We have an increase in power, but it's smaller than increase in performance, so we can say Riscy V2 has an higher energy efficiency. You can download the HDL of our core from our website, pulp-platform.org. It's written in System Verilog. And we are going to release Pulp, both all of IPAs, the SDK, the compiler, the cores, whatever you see in the system in December. But meanwhile, you can use Pulpino. And I want to conclude saying also we are open to collaborate with you. We'd like to receive your feedbacks. And we actually are looking for a verification support. So if you can help us to improve the verification of our system, it will be very nice. Thank you very much.
All right. Okay, thank you. Questions?
Hi, Steve Milburn from Draper. Did you guys do an energy analysis on bit reversal instructions to speed up FFT?
No, not yet.
No.
We are doing it. We are keep on working on it.
Lauri Kosken, Minima Processor. So is this also free and open, like RISC-V, or is there licensing?
What did you say, sorry?
Is this also open source, free and open? As
what?
Pulp?
Yes.
Yes.
It will be open source in December. It
Yes.
will be released as an open source platform in December.
All right, thank you.
All right, thanks.